Hello everyone. Today we will see lab program 6A of design and analysis of algorithms laboratory. The aim of the program here is to implement in Java the 0A 0/1 knapsack problem using dynamic programming method. So before we go for the program, let us see the two concepts. One is what is 0/1 knapsack problem, and then how exactly the program has been designed, then followed with the program execution and the output. So basically here we all know that knapsack problem, what exactly it means. So we have a bag of some capacity, right? And some items where each item has some weights and profits associated with it. I'm now supposed to fill the bag with those objects such that I get maximum profit and does not exceed the capacity of the knapsack. So this knapsack problem, there are two variants, right? Two types. One is fractional knapsack, the other one is 0/1 knapsack. Fractional knapsack is a problem which is solved using greedy method, wherein I am allowed to select fraction of the items. That means to say, I can either select 50%, half of it, or a 60%, or 1/3 of it. There's no harm. But in 0/1 knapsack problem, my option is only two, 0 or 1. That means to say, the objects can either be completely selected, means 1, or the item is not at all selected. So 0 means not selected, 1 means it is completely selected. Right? So 0/1 knapsack problem is a problem wherein the objects are selected completely. No fraction of the object is allowed to be selected. So the knapsack problem which I just stated, so given you have a knapsack with limited capacity and there are some items each having weight and the profit. So the problem here is now I'll have to find out which item should be placed into the knapsack such that I get maximum profit by placing the items to the knapsack. Maximum I'm supposed to get, and the weight limit of the knapsack is not exceeded. To be precise, we can now see that here the problem of finding the max value or the max profit is corresponding to the optimal solution. There can be several solutions, but I want the optimal wherein the profit obtained is the max. Right? So as I said, there are two variations of knapsack problem. One is fractional knapsack problem where the items can be selected partially or a fraction can be selected, which is solved by greedy method. The other one is a 0/1 knapsack problem where the item should be selected completely but not partially allowed. So you cannot select a fraction. And this is solved by dynamic programming approach, right? So to precisely tell me what is 0/1 knapsack problem, so I have just stated, given n objects, wherein each object has a weight and the profit associated with it, and a capacity of, total capacity of knapsack, capacity of m. The problem is basically to fill the knapsack with these objects in order to maximize the total value or the profit of those objects, packed without exceeding the knapsack's capacity, right? And here, the solution vector which we now talk about is x of I. So this x of I, which denotes the selection of the object I, which will be included into the knapsack, will be either 0 or 1. I mean, 0 means it is completely rejected, 1 means it is completely selected. So there is no fraction. So you cannot have 0.5, 0.6 and all those things. Fractions are not allowed. For every I, for every object ranging from first object to the nth object. So our intention is to find the values of x of I, that means to say which object is selected, which is not selected, and the maximum profit that I get, right? So this 0/1 knapsack problem, which is now solved by using the dynamic approach, involves construction of a table. So as we all know, the dynamic programming approach always solves the problem in bottom-up approach by constructing a table where a table contains the solutions of the sub-problems. So bottom-up approach means to say From simpler, I go to the complex problems, right? And solutions will be stored in a table. So what is that table now we are constructing is, we are constructing a table which we call it as a profit table designated as V, wherein the table has n plus 1 rows and n plus 1 columns. So what is that n plus 1 rows? N represents the number of objects or the items, one extra row compared to that. So 3 objects are there, 3 plus 1, 4 rows, and m plus 1 columns, which we call it as profit table. And these rows, n plus 1 rows are numbered as 0, 1, 2, 3, n. Similarly, m plus 1 columns are numbered as 1, 0, 1, 2, 3 till n. So the row indicates the object that is indexed with a variable called as I, right? So if I tell I equals to 1, it means the first object. I equals to 2 means the second object. So row represents the object. And column indicates the capacity of the knapsack. So j equals to 3 means currently the capacity of the knapsack is 3. So what am I trying to do is, I am breaking the problem into sub-problems, simpler sub-problems, where the capacity is 0, 1, 2, 3, increasing, right? And the objects are also increasing, 0, 1, 2, 3 to n, right? So now when I construct this rows and the columns, so I should know what are those entries in the rows and column cell, isn't it? So V of I comma j. So when I tell V of I comma j, so it means to tell that the profit that has been obtained when the knapsack is of this capacity j, and there are only how many objects? Objects from 1 to I. So you can see the knapsack is of size j, and there are only objects from 1 to I. So I represents not only the ith object, it represents the capacity from reaching from 1 to I, right? Number 1 to I, which has been considered. So this gives the optimal profit. So thereby, I should now construct this table, which we call it as a profit table, and then arrive at the optimal profit, final solution. Where is the final solution found? The optimal solution is now found. That is, your max profit is found at last row, last column. What is your last row? N. What is your last column? M. So V of N comma M gives me the maximum profit. Right? So such some example we have just taken where we have 5 objects and capacity is 6. You can see the V table looks like this. So you have how many rows? 6 rows because n is equal to 5, numbering 0 to 5. And how many columns we have? 7 because m equals to c, 6 numbering from 0 to 6. Okay. So I'll fill this. How to fill we'll see in the next slide. So I'll fill this where my maximum capacity, maximum profit is the last row and the last column, which I've indicated with red cell. So it is 13. The profit thus obtained is V of 5 comma 6, which is 13. This is all profit. See, all the cells here represent my sub problems, right? 13, right? And how do I get this 13? You can see this example here, right? The profit is 13. So how do I get this 13? By selecting the object third, right? The fourth and fifth. So selecting the third, fourth and fifth object, I now get 13 as my optimal profit. So how exactly we derive at this particular table, or how do we make the entries in the table? Is based on the recurrence relation. So as we all know, V of I comma j is nothing but what? The optimal profit obtained when the knapsack is of size j and the objects are from 1 to I being considered. With this knowledge, the recurrence relations, there are 2 relations which you have to consider. So V of I comma j. So anytime V of I comma j is equal to 0. So when I is equal to 0 or j equals to 0. That means to say, when there are no objects, I indicates what? Rows. Rows means objects. J indicates what? column. Column means capacity of the knapsack. So when I, there are no objects, V of 0 comma anything, right? No objects, obviously the profit is 0. When you have no capacity, say for example 5 comma 0, that will be 0, right? So you can see the table, right? So when I is 0, you can see, and I is 0, the first row is 0. Why? Because irrespective of whatever capacity you have, when you have no objects, the profit will be 0, right? Similarly, you see the first column, I can be anything, irrespective of the value of I. Capacity is 0, J is 0. So the profit remains 0, right? The next is V of I comma j equals to, I write V of I minus 1 comma j. So what does this V of I minus 1 comma j represent? So this condition arrives when the weight of the ith object is greater than j, right? So when weight of the ith object is now greater than j with respect to V of I comma j. So you are just trying to check whether I can put ith object in the capacity of j. So if weight of the ith object is greater than j, I cannot place the ith object in the knapsack. What should I do? I should not select the ith object, rather fill V of I comma j as V of I minus 1 comma j, means to say I'll have to just fill this with the weight, with the profit obtained by selecting I minus 1 objects with respect to the capacity j. So I is not included. Why? Because weight is greater than j. So V of I minus 1 comma j will be the profit here. So next is V of I comma j here. Next scenario wherein weight of the ith object is less than or equal to j. So the profit that I consider by selecting ith object being rejected here. Now here I should now consider the ith object. The reason because the weight of the ith object is less than or equal to the capacity j. So when the weight of the ith object is less than or equal to the capacity j, you will have to consider two scenarios. First scenario is profit obtained when ith object is not selected. You don't select ith object. Let's see what profit I get. Next is the profit obtained when ith object is selected. So two variations I'll take. Out of those two profits, I'll select the max one. Right? Profit obtained when the ith object is not selected. So what is that when ith object is not selected? What do you get the profit? V of I minus 1 comma j. So what do I get the profit when ith object is selected? So I will select the ith object. So what I'll do is, since I'm selecting the ith object, first put P of I. What is P of I indicating? P of I indicates the profit of the ith object plus, when I add ith object into my capacity j, what is the remaining capacity left? J minus W of I. So J minus W of I is my remaining capacity. Find out the profit from the table with respect to the remaining capacity, wherein the row is I minus 1. Why should I take I minus 1? Because ith object is added. So the remaining, that is I minus 1 objects only I have to consider. Ith is added. So I should consider the entry V of I minus 1 comma J minus W of I. So what does it mean? This will give me the profit with respect to the remaining capacity when ith object's profit is being added. So V minus 1 comma J minus W of I. Understood? The sequence you should know. Ith means the next previous object is I minus 1. So you cannot take here I minus 2, I minus 3. No, the previous only we should consider always here. So we are I minus 1, keeping I minus 1 objects into the constraint. Remaining capacity is J minus W of I because I added the ith object, right? So the remaining capacity will be J minus W of I plus the profit of adding the ith object. Out of these two, find the max. That is stored in V of I comma J. So you have to follow these three recurrence relations to fill the table. Once table is filled, the optimal solution is at the last row, last column. So V of n comma n. That is my optimal solution. That is a maximum profit which is being obtained. So now moving to the program. So we have only one class defined. So class so called as Knapsack DP, public class Knapsack DP, contains two methods. One is main method. The other one is a solve method. The solve method, you can see it has got four variables or four arguments. This holds the weight, T holds the weight, P holds the profit, indicates the knapsack capacity and indicates the objects, right? So it says this code will solve the zero and knapsack problem using dynamic programming. So what am I doing in this part of the method? I am just creating the profit table, extracting the maximum profit obtained, and which are all objects are selected. That I'll be doing in this method. Next is the main method, which will have the code, the respective code. Let us see how it works. So now we'll see first the main method. Let's just look at this. I created a scanner class object scan. So I created one object of class knapsack dp2 because I have to access the method solve, right? So if I create the object, I can access this method. If I want to access this method without creating the object, then you have to make this as static. Right now it is non-static, so I have to create an object. So I create an object here of the knapsack class. Print the problem statement here. Knapsack problem using dynamic programming. Ask the user to enter the number of items. He will enter n, which is number of items, by using scan.nextInt. So n is equal to 3 here, you can see. And then he has to enter weights and the profits, isn't it? So I have to create arrays. So you remember here. So the arrays that I create is weight and the profit, WT and P. And the array size, you can just see here. The array size I've given it as n plus 1, n plus 1, but not n. The reason because I am starting the indices from 1 here. Okay. I'm starting the indices from 1. So if I start with 1, so I need how many locations? N plus 1 locations. Because you know that in array, the index starts with 0. So if I give only n here, so I'll be able to access from 1 to n minus 1. That's all. Right? Because the index starts with 0, normally speaking in array. So since I'm starting the index with 1 here, so that the next part of the program looks very easier for me. So I'm just allocating one extra memory location here, that is n plus 1 and n plus 1. One extra memory location, right? Index is starting from 1. So 1 till n. If I start with 1 and if I here initialize to only n, then I can access here only till n minus 1. So I want nth location also. 0th first location till nth location. All right. So I need how many locations? N plus 1 locations. So I have initialized to n plus 1 here while creating. Right. After that, I'll read the weight. Again, store it in the weight array using a for loop. So profit, again, store it in the P array using a for loop. So I have taken this as my input. You can see here. So I starts from 1, 1, 2, 3, right? That's what I said. I'm not starting with 0, right? Next is asking the user to enter the knapsack capacity, which is stored in M. So I have taken an example where knapsack capacity is 4. Call the function solve, ks.solve, where weight is passed, P is passed, knapsack capacity is passed, and number of objects are passed. Next here is now the solve method. Okay. So I have two variables which is declared I comma j, which acts as a variables to the profit table, is index variables, right? So V, you can now see V is a profit table which has how many rows? N plus 1 rows and M plus 1 columns. So when you are initializing, be careful. Don't give N and M. So N and N, if you give, it can create only N rows, M columns. It is N plus 1 rows, M plus 1 column. So you'll have to initialize it in this way, right? So V to be initial is very important. This point you should remember, very important this is. If you lose putting plus 1, then it will allocate only n rows, m columns. So it should be n plus 1 rows, m plus 1 columns. Next is the solution vector x. So x is also of size n. So again, since I'm index is starting with 1, so I'm allocating one extra location here as n plus 1. Just for this convention, I have made my array to allocate one more extra location. Now, generating the profit table is the next task. You can now see I have to traverse n plus 1 rows, m plus 1 columns. Remember. So I have two for loops again where I starts with 0. Very much important. It should start with 0 because we have 0th row. The index of first row is 0. 0, 1, 2, 3 till n. J is 0, 1, 2, 3 till m. Isn't it? So for I equals to 0, I less than or equal to n, I plus plus. Very important this is 0 less than or equal to n. So if you put less than n, your last row will be gone. It will not compute. So your answer will be wrong. It should be 0 to less than equal to n. And here the second for loop for the column, for j equals to 0, j less than equal to m it should be. Remember, do not give both n because you are used to writing both sides m, right? It is not both m. So n plus 1 rows, m plus 1 column. So 0 to less than equal to n, 0 to less than equal to m here. Okay. So open the for loop here. Again, if no objects or no knapsack capacity, that is if I equals to 0 or j equals to 0. So V of ij is 0. Profit will be 0. Else if weight of I is greater than j, that is weight of your ith object is greater than the knapsack capacity j, you have to reject the ith object. Reject it. Don't select it. It cannot be selected. Reject it. The profit is same as selecting I minus 1th object with respect to the capacity j. Knapsack capacity j. V of ij is equal to V of I minus 1 j. Else, so there are three conditionals or three branches I can tell. Else, obviously, if this is false, weight of I is not greater than j means definitely it should be weight of I less than or equal to j. So it comes to the else part. So I should find max of V of I minus 1 comma j, which is the profit obtained when ith object is not selected, or and max of this and V of I minus 1 j minus the weight of I. So Wt of I, weight of I plus P of I. So remember how you should write the index operators. You can see V of I minus 1 close. This is row. J minus weight of I. This is another array. So weight of I, then close it. Like square bracket plus P of I. These two max values I'll have to find. So to use the find the max value, you not have to write a code. Rather than that, use a method which is present in the class math. So math is present in the util package, java.util package. So math.max. That's enough. It will find the max and store it in V of I. In the for loop, j in the for loop for the I. So the very important aspect here in the code is here the size should be n plus 1, m plus 1. Here it should be n plus 1 and here it should start with 0 less than equal to n and j should start with 0 less than or equal to m. Right? So you can now see here the table which gets generated. Can you see? I0 to n. So n is equal to 3, right? 0, 1, 2, 3. This is I. J equals to 0 to m. 0, 1, 2, 3, 4, right? M is equal to 4. So it will fill this knapsack problems profit table. So it will be filled. You can see. So using all those relations, it will fill. So it will execute how many times? So 5, 10, 15, 20 times. It will just execute and it will fill it. So once this filling is done, I will print the table. So something like this you can see. Printing the profit table is again for I equals 0, I less than equal to ni plus plus. For j is equal to 0, j less than equal to mj plus plus. System.out.println v of ij. Separate every entry of v of ij with a space, right? Columns are separated with a space, and I represents the row, right? Row, first row, all columns. After printing all the columns, given new line. Matrix printing, right? New line, and go for the second row. So it goes on. Second row, all the columns. Again, print all the columns, print a new line. So it goes on. It prints the table, right? The entire table. Then the optimal profit that is obtained is what? I should now print the optimal profit system.out.println. The optimal profit obtained is plus v of n m. V of n m. 1 second. Changes. Okay. So V of NM is the profit obtained. That is the last row and the last column. So you can see here, the profit obtained here is now the last row, the last column, which I have just highlighted in red. Now the next question is profit you got. But how do I know which objects are selected? So I have to know, right? Which are the objects which are now being selected? Let's look at this. So you have the objects 1, 2, 3 whose weights are this, profits are this. So 32 is the profit which has been obtained. So you can see in the table here which object will be selected in order to satisfy this constraint. You can just see the profits, right? If you see the profits easily, you can just get to know that the second and the third object is selected, 20 plus 12, right? Whose profit is now 32. And you can also see the weight of those objects. So 2 plus 1. 2 plus 1 is how much? 3, right? Where the knapsack capacity was 4. Still you have a space. But I cannot place this object. Why? Because I cannot place, its weight is 2. I could have placed half because 1 is still there, capacity. Isn't it? So 4, I have placed only 3. The weight of the objects are only 3. So 1 is there. So I cannot place half. Not possible here. So I can place completely or either I cannot place. So I have selected the objects 2 and 3 and the profit of second is 12, third is 20, wherein the total profit is now 32. So now the next question here is, now to find out which are the items selected. So we saw that it is the second and the third object which is now being selected. So I have to write the code for the same. So how do we know which are the objects selected? It's only via the profit table. So let's see how it has been done. So you can just see here, I just initialized I back to n and j back to w. Oh, sorry, m. So here I have taken m, the capacity of the knapsack. So you can see I is initialized to n, j is equal to m. So you can just see here, I is equal to 3, j is equal to 4. Yes, okay. So I will now know which are all the objects selected from doing some comparison from bottom to the top. Okay, so how it is? So I'll do something like this. If v of I comma j is not equal to v of I minus 1 comma j. So what is this v? V of what is I? 3, 4. I'll just write like this. 3, 4. Right? Is it not equal to V of 2, 4? So what is 3, 4? Not equal to 2, 4. What is 3, 4? If you can see here, right? You can just see here now. What is V of 3, 4? It is 32. And what is V of 2, 4? 2, 4 is 22. So you can see it is 22 and 32, the values. So this is 32 not equal to 22. What does it mean? Since the profits are not the same, they are not equal to, they are different. So if they are different, it means that the ith object is selected. Ith object. So see, this 22, it was previously 22. Next it became 32. It means to say that ith object is selected. That is which object now? The third object is selected. The third object is now selected. So it means to say now the third object is being selected. Right? That's because you can see here 32 is not equal to 22. That because since they're not, if it was same, that means ith object is not selected. Since it are different, the ith object is now being selected. Right? So how do I make that ith object? Since it is different, x of I, right? The condition is now not equal to, here condition is true. So x of I equals to 1. What is I? 3. X of 3 is equal to 1. So now what I'll do here is x of 3, which was now 0, it will now become 1. Okay. So I'll just change this to 1. Yes. So x of 3 equals to 1. Now, since my ith object is selected, I should now update J. So I should not keep the same value of J. What is J? You all know. There is the knapsack capacity. Now ith object is selected means to say that J should be updated. So what is the value of J? The value of J will be now equal to J minus weight of I. So it will be J minus weight of I. So J minus weight of I will be now updated. So what is J now? So J is equal to J minus weight of I. So J, which was now 4, 4 minus weight of I is now 2. 2, 1, 2. Yes. So weight of third object is 2. So that is equal to now 2. 2 is the remaining capacity because ith object is selected. Right? The why, if since the condition is true, right, it comes out and I gets updated. So if you update both J and I. So when do you update J? When ith object is selected, right? And you will update I when both it is selected or not selected. Both the cases we update it. Now I, which was 3, reduce it by 1. So I'll have to just find out whether now I equals to 2 is means selected or not. Okay. So the remaining capacity is only 2. I equals to 2 also. Now go back here. Again, you have a while condition which is to be repeated. So I keep repeating this when till I becomes equals to 0 or J becomes equals to 0. So I greater than 0 and J greater than 0. So now you can see here 2, 2. And again here it is 1, 2. Okay. What is 2, 2? Let us see what is 2, 2. 2, 2 is what? 12. Yes. And 1, 2 is what? Can you see? 1, 2 is what there? 10. Yes. 1, 2 is now 10. So you can now see here that again the values are different. The values are different here, which means to say that which object is selected now? The second object is now being selected. selected. Values are different. So ith object, this is I, this is I minus 1. So x of I equals to 1, right? So now I should make x of I. So x of 2 is equal to 1. You can see here x of 2 now becomes 1 and update j. So j. So you can now see the weight of the second object is 1. Weight of the second object is 1. So 2 minus 1 is equal to 1. And I is also now what? 2. Now minus 1 because I have selected second object. I have decided selected or not selected. So you can observe here now I is 1. J is also 1. Again, go repeat it because I have J. Any one should become 0. Right now both are 1. So again we can now see. Here it is 1 comma 1 and here it is 0 comma 1 comma 1, 0 comma 1. Let's see what it is. 1 comma 1. Okay. Comma 1. 1 comma 1. It is now what? 1 comma 1. So you can now see here 1 comma 1 is now 0 and 0 comma 1 is also 0. So actually while typing it has been typed as 10. So actually this is 0, right? So 0 and this is 0, right? So you can see now both the values are the same. So my condition here is not equal to, right? So they both are same. So why if does not execute, comes out, I gets updated. Now I, which was 1, becomes 0. See here, I which was 1 now becomes. Now here you can now see, it again go back to the while. So I greater than 0 and j greater than 0. We can now see that I has become 0. So the while gets terminated. And you can see the array X will now hold the items which have been selected. So you can now see the X array here. 0 indicates item is not selected and 1 indicates that the item is being selected, right? So you can see which are the items which are selected, 2 and 3, because X of 2 and 3 is equal to 1, right? So system dot out, I'll just print now, system dot out dot println items which are being selected, I is equal to 1, I less than equal to ni plus plus. If X of I equals to 1, so I'm just printing which are selected. If X of I equals to 1, system dot out dot print I, not X of I, because if X of I is 1, X of 2 is 1 means 2 second object is selected. X of 3 is 1 means third object is now being selected. So 3, right? So print only I here, very important. Don't print X of I. So if you print X of I, you will get only 1 1 as the answer. Which objects or which items are selected? If X of I equals to 1, print I only. Okay. System dot out dot println. So the very important aspect of the program here is with respect to generating the profit table. How do we generate? So you should be very careful here. As I've told you, here it should be n plus 1 and m plus 1. Very important. And the X array is also of size n plus 1. The profit array and the weight array are also of size n plus 1. Okay, one way of doing, right? So you can also see the profit table which is now being printed, and the profit table looks like this. So let us now execute the same onto the compiler and see whether we get the same answer as we have got here. Okay, so let us now see the profit table which we have got here along with this, right? Let us see how it is done. So it is again the same, the X array which gives you the elements there. So now let us see the program. So the program is here, same program which I have given. So just execute it. So how many objects we have given here? 3 objects. And the weights are one by one. Enter the weights. 2, enter 1, enter 2. Then the profits 10, 12, then 20 was the profit. The capacity was 4. You can see the profit table is this. Okay, 0, 0, 0, 0, 10, 10, 12, and all those things. And optimal profit obtained is 32. So in the execution, in the explanation, this second row, second column was 10. That was because of the typing mistake there, but it's actually 0 there. So 0. So the optimal profit obtained is 32. We can see. And the items selected are selected. Second and the third item is being selected. So now that is what it has now been to, right? The enter the weight, profits. These are all the statements you can vary. It's not a problem. The variable names also you can vary. You not have to use the same variable names, right? And how exactly you deal depends on your uh, peer understanding. Mere understanding. Okay, the second and the third object is now being selected. You can see the profit also, which is 32, which is shown here, right? Thank you.